Oh my God, Chapter 21, Comparing Two Proportions. We started this in class back before spring break and your extended absence. We actually did part 1 and part 2, which is basically confidence intervals. We do need to talk about the assumptions. If you've already done that part and you were there that day, go ahead and skip forward to part 3. Got a little bit to add on there. This is not as complicated as it looks. I wonder if that guy's wearing a seatbelt. I sure hope so. So one of the things when doing two proportions is that they do need to be two independent proportions, independent from each other. And one way to understand that is to look at things that are not independent. Like if you were sampling, doing a taste test and comparing the proportion of people that prefer Pepsi. Oh, say that 20 times. Compared to the people that prefer Coke. So the reason that not independent is because if more people prefer Pepsi, then that automatically forces less people to prefer Coke. Then if one goes up, the other has to go down. So that is not independent. Same thing, like if you look at the beans in my bucket, if I pull out a handful of beans and more of them are white, then that means less of them are red. Not independent. However, if you grab some bag of M&Ms and you count how many red ones and you compare it to a group of red Skittles, the entire bag of M&Ms could be red, and it would have nothing to do with how many red Skittles there are. That would be independent. That's the kind of thing we're looking at two proportions that are completely different from each other. And of course, as we have had to do with all of our p-hats and proportions, you have to check your 10% condition, which a lot of the problems that it's kind of obvious that there's not really a lot that you have to go through and check, but you should be checking it for both proportions. That means instead of like 3 things to check, you have to check 6 things. Your 10%, your sample should be less than 10% of the population, and you should have at least 10 successes and 10 failures. You can kind of tell that part pretty quick just by looking at the numbers, because they often give us the number of successes and the sample size. Not always, but often. And of course, our data should be collected randomly and without bias, as always. Often, in a textbook setting, you really just have to assume that that's what they did. We just really don't know. Okay, standard deviation for comparing two proportions. This comes from back when we did adding or subtracting standard deviations from 2 random variables. The fact that they are proportions doesn't have anything to do with that. You are still going to square the standard deviation before you add them and then take the square root. That's kind of the Pythagorean theorem, is kind of a reminder that you have to square and then add. Even though we're finding a difference, you still add. And so when you do this for proportions, the standard deviation of P1 is P1 times Q1 over N1, take the square root of all that. So when we square it, it gets rid of the square root. Then you add them together and take the square root. Kind of looks kind of like an ugly little formula there, but it's not that bad. I mean, we can, make it worse by putting hats on everything. So what we do is we switch over to our sample instead of the actual proportion, because we don't know what the actual proportion is. So if we use our sample, we'll call that our sample error or standard error. And it's just using the hats instead of the p's. Which means if you're going to do a confidence interval, this is very much like what we did before. It just looks more complicated. Z star is still the same critical value it's been the entire time. The interval for us will always be about the difference between two proportions. And then you're going to do plus or minus Z star times the standard error, which is just a bigger, uglier equation. It is actually not as bad as it looks. So here's a quick little example. 2007, a study in Massachusetts found that 70% of women wear their seatbelts while driving, no matter who the passenger was. However, for men, it appears that the seatbelt wearing depends on the passenger being male or female. In this study, 66% of the 4,208 men driving with a female passenger wore their seatbelts. while only 49.3% of the 2,763 men driving with other male passengers wore their seatbelts. So we're going to find a 95% confidence interval on that. There it is, plugged in all those numbers. That was quick. Our 66%, and that's our P1 and our Q1 divided by the sample size, 4,208, plus P2 and Q2 divided by the sample size. Multiply all that out. This is the difference, is 0.167, and all of this together gives us that, which means this is our margin of error, 0.0235. If you go ahead and do the subtracting and then adding, and then I switch to 2%, so that is our interval from 14.3 up to 19.1. So somewhere in that interval is the true difference of these two proportions. If we're going to do it with a calculator, which is what I'm going to do, I'm certainly not going to calculate that out by hand. First, you want to press the stat key on your calculator and then arrow over to the right to where it says tests. When you do that, we have a whole list of tests, and there are quite a few of them over there. We are going to arrow all the way down until we find two proportion intervals. One thing to remember is that the intervals are below all of the tests, so you have to get down quite a ways. And then, because we are doing a z interval, because it's z star, and because we're doing two proportions, so you should know before you pick up your calculator that you are looking for two proportion z interval. Anyway, when you press calculate, when you select your interval, you now have to enter your x1, your n1, your x2, your n2, and the confidence level. So x1 is the count of successes, and n1 is the sample size, and the next two will be for the other one. You get to choose which one is 1 and 2. I was doing the larger one, with women in the car, the 66%. It's going to be my 1, and the smaller one, the 49.3%, for number 2. Typically, because if you subtract those, you get a positive value. They didn't give us the counts, though, so we have to figure that out. So 66% of 4,208. And that's what you get. And then the other one, I went ahead and did the percentage there. Now, if you scroll down and hit calculate, your calculator is going to burp, because your calculator knows that that is not the count. That has to be in a whole number. Both x1, x2, and the sample size, all four of these have to be integers, not decimals. So you do need to kind of work back up there and round off to the appropriate number. And then you can come down where it's blacked out there. That is the calculate. Hit calculate, and boom, there it is, the interval. And if you haven't calculated it before, you would actually get the proportion and then also the sample size. But that's the interval. If, let's say, you're doing this in your calculator and the question asked for the margin of error, well, it didn't give us that, but you can find it actually pretty quick. Just find the difference between those two numbers, which gives us the total width of the interval, divide by 2, because the margin of error is only half of it, and then that gives us the same margin of error that I calculated before by hand. Pretty handy. Definitely a lot quicker on the calculator, and the expectation is that you will start using the calculator to do this stuff.